the derivation of the Heron methods is also based on the Taylor series expansion. For example, for the second order Runge-Kutta method, that is the Heron method's second order Runge-Kutta method. The standard format here, okay, simplified, okay, K1 equal K2, this one, and then the coefficient C1, C2, P1, Q11 are the constant to be determined. So to derive the Heron methods, we need to determine this coefficient. So here the solution of the second order, we plug K1, K2 here into this, then we get this. This is the solution of the second order RK method. Then based on the Taylor series expansion, we can write down the formula, Taylor formula. We keep the second derivative term, the first derivative term and the second derivative term, and eliminating the remaining. So we write down in this way. Then we can determine the local truncation error here. That is the yi plus 1 of the Taylor series minus y plus 1 of the RK methods. So simply, then we get this. This from the previous slide, okay. Then we have all this, right? Y1 and first order derivative term, second order here, okay. This is the second order. And this term can be determined by taking the binary Taylor series expansion at this. So this is another Taylor series. And then we plug in all this into this equation C. Then we get the local truncation error. So here it is, the local truncation error. And then simplify in this way, and then here. This is the simplified of the local truncation error. Next, we are going to calculate the total truncation error using the local truncation error. So assuming C equal 1 over 2, then we get all the other parameters in the previous slide, and then we plugging back into the K1, K2 formula, etc. Then we get K1 here, K2, and so this is the final Heron methods. Okay. Now let's look at the fourth order Runge-Kutta methods. This method has very high order accuracy. Has 4 order. You see 4 order. So here summarize the iteration. See yi plus 1 equal yi. See that this is the slope times step size. So the slope, you see, is actually a combination of K1, K2, K3, K4. Okay. K1 equal the slope of the Euler method, right? This. And K2, the same as the human methods. And the K3, you see, based on the K2, using K2 to calculate K3. And then K4, use K3 to calculate K4. Okay. That is, use this to calculate K4. Calculate K4, the K3. Stiff ODEs. This is a special ODEs. Look at the definition by Wikipedia. A stiff equation is a differential equation for which certain numerical methods for solving the equation are numerically unstable, unless the step size is taken to be extremely small. So, if the step size is not so small, is not extremely small, then the stiff ODEs cannot be solved. Look at this example. Okay. The special case here, 100 and minus 1000 times y. So this number is very large. Okay. Look at the analytical solution. Look at here. This very steep. Y changes with time very quickly at very short time. Zooming this part right here, you see the time very short, right? From 0 to 001. Here, in very short time, Y increase quickly. So, very just like a, right? Very quickly. Now let's analyze the stability. So again, this is the equation, ODE equation. And the homogeneous part, actually just keep this term, okay, eliminating the other term. Then we get the homogeneous part here. Here A equal 1000, a large number. So this form is similar to the stability formula for the Euler method, right, in the previous slide. So the condition for stability when Euler method is used is here. A less than 2 over A. You see, this is very small step size. A less than this one if you want to get it converged. Otherwise, it's not stable. For the system of ordinary differential equations like this, several ODEs, given n initial condition for n ODE, then the previous methods, Euler's method, the Hilbert method, and the fourth order RK methods can still be used for solving these equations. Okay, just use the same formula.